Just wonder what is going around you, and I'll be simple. Okay, so what did we do last time? So we looked at the L-square operator, right? Angular momentum in details. It's also a solution for a particle on a sphere. And so why are we doing all this? You guys remember? Yeah. Yeah, we're trying to get to the hydrogen atom, right? Just a puff is not really simple and straightforward. So let me just remind you. So what's the Hamiltonian for hydrogen atom? The last system, promise you, last system. We're going to be addressing in this semester, in this course, right? And so what do we have? Usually kinetic energy plus potential energy. Kinetic energy is minus h bar squared 2m, and then Laplacian for electrons, and potential energy is just 1 over r. Okay, so sometimes the potential energy is written in a different coordinate system or unit system, and the simple expression that is relevant to atomic units becomes somewhat more complicated. Well, Z is essentially 1 for the hydrogen atom, but for hydrogenic atom, it's when we have 1 electron and some nucleus of the positive nucleus, charge Z plus, right? Then Z will be in the potential with a minus sign, and then the charge of the unit charge of the electron and the nucleus, then 4 pi epsilon 0 and then 1 over r. So essentially all that becomes just minus 1 in atomic units. Okay? Just the simplest units for atoms, molecules, and in general in quantum mechanics. Okay? So this is our Hamiltonian, right? And the way we try to solve this problem is we essentially went in what system of coordinates? So what system of coordinates do you know? Huh? Polar. Polar coordinates in 3D, how do we call them? Spherical, that's right. Why did we go in the spherical coordinates? Which part? Kinetic or potential? Potential, right? Because in spherical coordinates, potential part is just 1 over r. The kinetic part, though, is somewhat more complicated. Okay? So I'll write down just a part of it. So kinetic energy in spherical coordinates, the constants are there. And then we have Laplacian written in the following form: 1 over r squared d over dr bar squared d over dr plus 1 over 2 mr squared. Here, operator of the angular momentum squared, so it's Lx squared plus Ly squared plus Lz squared. And we were talking last lecture how to find its eigenvalues and eigenfunctions. We established that there are eigenfunctions which are called spherical harmonics. They depend on theta and phi. Okay, theta and phi. These are angular parts, all right? And this is a radial part. And we established that in order to solve this equation, L times L plus 1, h bar squared, YLM, theta phi. Right, so we learn how to solve this equation. And today we will address the whole hydrogen problem, because now we have a solution for L squared, and we will build the solution for the total problem. What we're missing right now is what part of the solution? If the total wave function will be written in 3 coordinates, so the coordinate that is angular function that corresponds to angular coordinates is the spherical harmonics function. And then what else is left? The radial part, right? Radial part depends on the coordinate small r. And today I'll just show you how to kind of obtain this part. Now, the way it's done is very similar to what we've been doing before. This is the equation. It's all notes. You don't need to copy it. They're available online. Just try to understand what's the meaning of all this. All right? So what do we have? We have a part of the solution that kind of helps us to solve for this operator, but we need to deal with t. T has this extra part, then it has this function, and also we have the potential part, which is minus 1 over r, right? So to make it more in an algebraic form rather than this complicated looking form that involves derivatives, like in operator form, Hamiltonian is equal to kinetic part plus potential part. Now potential part is equal, kinetic part can be written as some operator of r plus some function of r multiplied by L squared. That is dependent on theta and phi. Right, so essentially I copied this expression in this form. What this form tells me is that I put hat so that just to show that this is an operator, so it has some differentiation in it. This is just a function, so it doesn't have any differentiation, it's just a multiplication by a function. This is also an operator, and we know how to treat it. Okay? Now the total Hamiltonian will be then the radial operator plus function L squared plus, we can say plus minus 1 over r. Right? So essentially we can say that the form is some operator output A, which combines this guy and this guy, plus some function B, well, let's call it f, keep it f of r, L squared, which is theta phi. right? So does this look familiar? Yes, no, that's a simple question, right? Does this look familiar? No, it doesn't. Okay, but it should, because when we were considering L square, I was solving this problem as A plus B times LZ squared. Remember that? Yes, no? You remember, right? And B was actually a function of theta. LZ was operator that was acting only on phi. A was operator that acting on theta. Okay? And so this form allowed us to formulate eigenfunctions of L square as eigenfunction of LZ multiplied by some extra function. And this is pretty much the same. So how do we do this? No, it's just you don't need differential equations. Well, you end up with differential equation, but the idea here is the form is the same, and if you want to find the Hamiltonian eigenfunction, then you can use eigenfunctions of L square, right? Before, remember how it all started? We started with LZ, right? And LZ was very simple. It's minus I d over d phi, particle on the ring, right? Particle on the ring in the polar coordinates. Essentially, our whole kinetic energy or Hamiltonian of the particle on the ring was proportional to LZ squared, right, with some constant. Then we solved this problem, h, say psi equals E psi, for the LZ functions. Then we consider, okay, so what's going to happen if we put particle on a sphere, right? So phi is here, and then the theta be another angle here. And then we found that particle, and this is on the ring, then particle on the sphere, the kinetic energy, because there is only kinetic energy for the Hamiltonian, particle on the sphere, the kinetic energy was some constant L square, right? And that constant, it was something that depended on the radius, right? Here is also this constant dependent on the radius. But that's not essential. The essential part is that we again found the equations for the L square, which are eigenfunctions of H of particle on a sphere. How did we do that? We used this, that L square actually looks like a sum operator of theta plus some function of theta multiplied by LZ square phi. And then for particle on a sphere, we use particle on the ring times some function of theta. Okay? No recollection? You remember that, right? So the same procedure we do again, all right, here. Because the whole Hamiltonian is, again, some new operator function times the old operator. Okay? So what do? We now allow radius to change, and we write down that the wave function for the hydrogen atom is equal to y depends on L and M, theta phi, then the radial part. Okay? So then we put this into the form like this. So what is this? So radial operator plus function of r L square. This is our hydrogen atom, essentially Hamiltonian, and it acts on psi equals E psi, right? So then we have y lm a r plus f of r L square y equals E y lm. What else? R. Right, so what can we simplify here? Can we simplify this? Yes, no, who thinks yes? And you think no, right? It's very simple. The faster you answer, the sooner we'll finish this. What's the point of sitting? I'm not taking the points for wrong answers, right? Or you need more time to think? No? Yes? More time? Okay. Whenever you're ready. This one? L squared and y. How do we simplify it? That's right. Can we simplify anything else? Not really. Yeah, because this is some unknown function yet. So we can simplify this as L plus 1. That's the eigenvalue problem that we solved last time, right? So what did we achieve? Why is that simplification? Because we essentially get rid of the operator here, right? So we don't have any more operator that that acts on the theta and phi. We have now just a function y instead of the whole expression with the operator, right? And so what can we do now if we look at where do we have y? We have y in the left-hand side and y in the right-hand side, right? And this is exactly the place where, you know, if someone asks you how to solve Schrödinger equation before you've taken this course, what would be the simplest solution? Seems like there's someone is smiling, so probably someone is getting this joke, right? No, you don't? That's right. So you just cancel, right? Of course, it's a joke. It's not the solution. because, well, Hamiltonian is an operator, and after taking this course, I hope you all understand that. So it modifies the function, and what is said here is non-trivial because the action of h is different than the action of e. E is just multiplying by a number, h is differentiating, multiplying by some other function, so you cannot just kind of divide by psi, otherwise you're going to get the operator equals to number, so which is clearly wrong. Or let's say it's not right, you need a function there, because operator and number, those are two different objects. Okay, but here we got rid of the operator that acts on y, so now it's a function without an operator, and that function is on the left-hand side and on the right-hand side of the equation, so we can easily cancel it without any consequences. Right? So it just simplifies the whole problem, because now we have eigenvalue problem on a function which depends only on one variable, r. Right? So we have this a complicated operator that comes from the kinetic energy plus function of r, some other part. It's right here. This is the function of r in front of the L square. Right? So this function of r, what else do we have? And we also have that function of r is multiplied by L plus 1, right? So that forms another operator that acts on our unknown function big R of small r, and this is equal to the final eigenvalue and the function. Okay? So that's the radial equation. Okay? And it's pretty much the same technique as we use to obtain the spherical harmonics, because in the case of spherical harmonics, instead of L square we had Lz, and we did the same kind of factorization. So now it's 1D equation, and as with spherical harmonics, I'm not going to go into the solution of that equation. All we do is just we state this is the full form of the equation I wrote with all the parts. This part is the A operator. Our L square is not removed yet. It's just the beginning, and then we put our spherical harmonics here, which are eigen functions of L square. Right? We know what eigenvalue is. It's L times L plus 1. And then we obtain this equation that I wrote here in the explicit form. This is A in my notation, and this is function f of r multiplied by a constant, L times L plus 1. And then there is an extra potential. Okay? That is a part of big A operator. Now this has a solution, and we now look at the first part of the solution, the eigenenergies. Essentially, all the solutions will be enumerated by principal quantum number n that you've seen already in general chemistry, right? So it is 1s, 2s, 2p, that sorts of stuff. So 1, 2, 3, those are the n's, the principal quantum number. Don't confuse that with the orbital angular momentum number. And m as well. M is the projection of angular momentum. Now what do we have here? The bunch of constants right here, which all become 1 in atomic units. So I'll just clarify what the energies are. Energies, they depend on n, and they look like minus because everything is below 0. What 0 corresponds to is when for any molecule in your calculations in the lab or for the hydrogen atom. 0 is when all electrons are separated from all the nuclei far, far away, okay, to infinity. So that's 0. When you bring them together, energy goes down and becomes negative. Right? That just means that in order to disassemble molecule or atom, hydrogen in this case, you need to pay the energetic price, right? So you need to put some energy. So the graphical representation will be like this. So we have the radial coordinate. This is the potential minus 1 over r for the hydrogen atom. And it goes to minus infinity, right? Because when r approaches 0, it goes to infinity, and there's a minus sign, so it goes to minus infinity, essentially, right? But we talked about this, although potentially in terms of potential energy, electron in a hydrogen atom would be the most stable at 0, but because then it would be really, really squished by the potential, kinetic energy would go up, and that in reality doesn't happen. So the first eigenenergy, which corresponds to n equals 1, right, is, let's keep the z here, z squared 2n squared. That's the form of the energy in atomic units, where all the constants in front become 1. And so in this case, E1, the first energy, is the lowest energy, and it's 1 over 2, right, where we assume z is equal 1. Okay, so this is minus 1/2. And if you do Hartree-Fock or DFT calculation, then on a hydrogen atom, in the exact theory, which Hartree-Fock and DFT should be potentially, if there are no approximations and the basis set is complete, then for hydrogen atom you should be getting energy which is 1/2 in the minus 1/2 in atomic units. Okay. Then what else is known? Interestingly, the energy doesn't depend on L. So in a hydrogen atom, we have a energy diagram which is 1s, 2s, and then 2p, and then there will be what, 3s, right, 3p, and 5d, and so on and so forth. Sorry, not 5d, 5 orbitals of 3d, right? But energy-wise, they all will be the same because the energy depends only on n, not on L. L, on the other hand, is bound by n to be between 0 and n minus 1. That's why we have 1s, where n equals 1, L equals 0, and we don't have 1p, right? Because p would correspond to L equals 1, therefore you need n equals 2, so on and so forth. That you probably already heard millions of times, right? Okay, good. So this is the diagram. So what happens when we climb up this potential wall is essentially we have more and more diffuse functions, right? And at 0, or n equals infinity, so if you put n equals infinity here, you get 0. You start the so-called continuum states, the states of the free electron in the free space. So electron doesn't really fill the nucleus anymore. It's rather just free in space and has a, like, whatever energy it has above the 0, that's the energy, that's kinetic energy, and it's a free electron essentially. Okay. Right, so then there are these historical units, or essentially explanation what atomic units of length is. That's the Bohr radius, and that goes back to theory of Bohr, which we don't study here because Bohr essentially tried to save the classical theory and introduce a bunch of assumptions that were kind of ad hoc in the sense that they were not based on any theory. He was just using them, prohibiting the classical electrons to fall on the nucleus, and since he was using classical mechanics, which necessarily led to the contradictions, then he needed to use these artificial constructions, but yet they were taken as some guiding principles guiding in terms of units, right? So for example, Bohr radius is the unit of length, and there is just again set of constants that has unit of length, and it's approximately half an angstrom. That's 1 Bohr, and we can use this unit of length in the energy expression, but as I said, the most convenient units when we talk about atoms and molecules, those are atomic units, and in those units A0, the atomic unit of length, is just 1, and all the prefactor in front of energy is also 1. Okay, so this A0 was obtained in the Bohr theory as the radius of the radius from the nucleus where the electron is orbiting, but it's not so far from the truth after all. That's why it was left in the theory as some unit, because A0 is most probable distance between the electron and the nucleus, and that we will be able to confirm by just looking at what's the most probable distance between electron and nucleus. You need to take a wave function and consider what's the average R value, right, which is average of R operator with the wave function. And if you put the 1s wave function there, then you will get A0. We will get to that either today or next lecture on Wednesday. Okay. Now units of energies, those are Hartrees. Those exactly the units I used here to write down the expression in this very simple form. And there are some conversion factors to electron volts and joules, kilojoules per mole, those sort of things. Right, and then this energies of Hartrees, the hydrogen atom energy is -1/2, which is kind of convenient. Now there is another historical thing, Rydberg constant, that is another set of constants in front of the z squared divided by n squared. It's as you can see in atomic units of energy, Rydberg is 1/2, right? Because energy should be in atomic units z squared divided by 2n squared, but Rydberg is kind of taking this 1/2 inside. But Rydberg constant is given in wave numbers so that it's more convenient for spectroscopic calculations. Okay. Now there are these two different Rydberg constants depending on whether we consider in hydrogen atom in the situation where we think of the nucleus as just a center of universe or center of this system, right? And we do not allow it to move. More accurate consideration would consist if we look at the problem as a two-body problem, like in the solar system, right? You have a sun and other planets, right? So one way to look at this is that the sun is just in the center and others are just rotating around. So we have a radius for each planet, and sun is considered to be a static but in reality, it's a more complex system. Even if you consider just the sun and one more planet, that's a two-body problem. And in a true accurate consideration, you need to separate center of mass, which is a static point between, like if you have two similar mass particles, then the center of mass will be somewhere in between, will be exactly in between, and then there will be kind of a coordinate system from the center of mass where one coordinate would correspond to the coordinate of center of mass, and another coordinate would be the relative distance of two particles. So in that more accurate consideration, you can separate center of mass, motion of the two-body problem as a whole, and then you will have just essentially the motion of or dynamics of this internal coordinate separated from the center of mass. And if you do that for the hydrogen atom, which is more accurate consideration, then you get the Rydberg constant, which is written here. So now comparing these two, you can see that they're very close. They're different in what about a tenth of the centimeters, inverse centimeters. So this is it's very small, considering. I don't know which units are you preferring, but this is kind of, I guess, chemical accuracy is kcal per mole, right? So this is much lower than 1 kcal per mole. That's why people do not make a really big deal about the, well, like Born-Oppenheimer approximation that is used to consider the static nucleus is considered to be very accurate, and that's confirmation of that fact. Now, what can we do with these equations? We can characterize the spectrum of hydrogen, which was a big deal in the beginning of 20th century, because what was found is that, well, experimentally it was found that only certain wavelengths were obtained. If you excite hydrogen, then it fluoresces light, and those fluorescent radiation was detected. So these gentlemen, they kind of they were characterizing certain subsets of the spectrum, and they were like, these subsets were then named after those gentlemen, right? But once the total quantum theory was created, then people realized, oh, this is just a consequence of frequency coming from the hydrogen atom radiation should be related to these two numbers, the initial and the final quantum numbers in this way. Well, these early kind of investigations were done just purely numerical. So you have a spectrum, and you try to kind of see what kind of progressions do you have. Just purely numerical. You have some numbers, and you try to approximate them. That's what this gentleman did, and they got into essentially history of science, right, by just doing that. So you can see getting your name in a textbook wasn't that difficult that time. Okay, well, right now it's much harder. Okay, so the equation is very simple, and they didn't yet, well, they kind of obtained this just purely numerically from just playing with the spectrum. Okay, so what else can be said about this? Yeah, let's just consider a simple problem, which could be one of the problems on exam. And the problem is, let's calculate the wavelength of light emitted when electron falls from the 100th orbit to the 99th orbit of helium plus ion. report answer in the centimeters, and assume that the nucleus has an infinite mass. So there are two differences, two features here. That first, it's considering the helium plus atom. This is not harder than the hydrogen. All you need to be careful is with Z, that it's not 1 anymore. It's rather 2 for helium, right? And the fact that it is said that we should assume the infinite mass, then that means that the certain Rydberg constant we should consider. It's this one. And then we just need to be careful that we go from the 100th to 99th level. And the expression is relatively simple. Oops. Knowing all these constants and putting the numbers gives you the wavelength, which is very small because, as you can imagine, 1 over n squared, it kind of saturates close to the higher you go, the smaller the distance between the levels. And there is it's not just like that accidentally. You can think about these problems if we look at the progression, say particle in a box, harmonic oscillator, and then this hydrogen atom, which looks more like this. If we think about R is only positive, and here we use X, right? So the idea here is that you can see the potential is either convex or concave, right? And particle in the box can be thought as x to the power n, where n goes to infinity, right? So some potential like that, right? If you have you ever played what happens if you take x to the power n and then start increasing n, what happens to the graph? It becomes, if n equals 1, say its modulus, it's like this, and you start increasing n squared, it has a more concave form, and then if n goes to higher and higher values, then, the fourth power already will be like this, and so on and so forth. They become more like a box. You can try it at home. Between 0 and 1, anything, say, if you start with 0 and this is 1, this is minus 1, right? So anything between 0 and 1 will be essentially flat, because you're having like 0.9 into the 100th power becomes very close to essentially 0.1. And if you increase the power, then it will be even smaller value. So the higher the power, then the closer you are to a 0 line, right? But my point here is that we this is the most concave potential. This is less, and this is, this was convex, and this was concave, right? So here we have energies that are proportional to n squared. Here energies are proportional to n. And here the energies are proportional to 1 over n squared, right? So it's kind of the more concave, the higher the power of n. Less concave or more convex, then we have 1 over n, right? Okay, and so that's a summary of for the eigenfunctions. All right, so we have the following relation: 3 coordinates of the spherical system, 3 quantum numbers, n, l, m. Essentially, n is coming into play in the radial part. L also plays a role in the wave function, but not in the energy. That's why we have big R with n, l, depending on small r. Then we have a spherical harmonic, y, and the relation between quantum numbers, which are written here. And you've seen that already probably many, many times. Okay? Any questions? Good. So there's a first table. What's this? Wave function for the hydrogen atom. That's how they look. This one is the s orbital. As you can notice, they all have this rho is a distance defined, r divided by a is 0. That's why a is like this atomic Bohr radius is a very convenient quantity, and it's convenient to kind of measure distance in it, because then in the wave function you have this rho instead of r with division by the Bohr radius, right? So this is 1s, then you have 2s, 2, 0, 0, and then 2p. Well, here yet we have not real eigenfunctions, but rather just complex eigenfunctions that we can combine together in order to make them real, the one that printed in the textbooks on general chemistry. All right, so, and then there are these letters that, yeah, we all saw, right, as PDFGH, with examples on the kind of how one notation goes to another. Okay, so now in chemistry we usually interested in how large the orbitals are, so that depending on the distance between atoms we can say whether the bond is well formed with these orbitals or poorly formed, right? So to represent orbitals, what is convenient to do is to reduce the number of coordinates, because you have 3 coordinates are like essentially 2 angular coordinates and 1 radial. So what people usually do, they plot this probability density isosurfaces where the radius is fixed, so that essentially a certain probability density is encompassed into this isosurface. So the smaller radius correspond, for example, in this case, to having a half of the, if you integrate the whole size square, right, and that would be 1. And then if you have a certain radius, then the integral if you go from 0 to some r1 essentially, then with the part of Jacobian, right? So then if you get, say, 0.5 here, that radius will be used to represent the orbital. So the radial part is fixed onto the value that gives the probability of finding electron within that sphere 1/2, right? While the whole integral, if you go from 0 to infinity, psi squared r squared dr. We'll talk about this a little bit more. Then the whole integral is 1. And this r squared comes from Jacobian, because we are now integrating in the curvilinear coordinates, not in the Cartesian coordinates. And all other like angular coordinates are considered to be integrated. Okay? All right, so these are just explanations on how do we go from the real, or from the imaginary to real wave functions, because originally they come out in, say, this form, where what do these exponents correspond to? This exponent of I phi, where do they come from? Huh? M, that's correct. But what operator do these eigenfunctions correspond to? The exponent of I phi. Oh, what operators do you know, really? You don't know more than 5, right? Just go by the list. Okay, that's 1, but that's for the whole function, right? Hamiltonian. Okay, you can go with Hamiltonian, but Hamiltonian of what problem? Because there is a Hamiltonian for which this is an eigenfunction, and we studied it in the beginning of our route to the hydrogen atom. That was Hamiltonian of particle on the ring, and this is an eigenfunction for Lz. Right? So, wait, how many operators do we know really? Huh? Hamiltonian. What else? Kinetic energy. So, huh? Potential. Angular momentum. Momentum. Position. 6. What else? Well, there are 3 components of angular momentum. What else is important about angular momentum? What other, like, what's the combination of those components in a certain way is important because it commutes with all other components. L square, 7. What else? Do we know anything else? Huh? Laplacian, which is kinetic energy, pretty much. So you see 7 operators. It's not that many. And the last operator we will study on Wednesday is spin, which is kind of a it's kind of could be thought as generalization of angular momentum, just different variables. Anyway, so this is Lz. Oh, sorry, Lz. Yeah, it's Lz eigenfunction, because in the spherical or polar coordinates, Lz is minus I h bar d over d phi, and then Lz exponent plus minus I phi. What do you get? You get h bar here, and then the exponent plus minus. Right, so this part is coming from the fact that the hydrogen atom, right, Hamiltonian, L square, and Lz, those 3, they commute. Okay, they commute. That's why they share the same system of eigenfunctions. More than that, we build in the eigenfunction for H is just a product of eigenfunctions for Lz, for L square, and the radial part. But this exponent of I phi, according to Euler expression, they produce the real and complex part. Now it's not fun to have complex functions, or at least people kind of suspicious about them, right? And that's why for chemists, physicists kind of put together the linear combinations that are real, and so that's how you do them. Say if you have essentially what comes out of the hydrogen atom problem is not px, py, but rather p plus 1 and p minus 1, right? Those are the functions, and p0. P0 goes directly to pz, but then px and py, they are coming out of p plus 1 and p minus 1. Why p0 is real? Why don't we need to do anything with p0? Well, 0, what does it correspond to? Here, we have this m number, right? Truly it should be im phi, right? And if we put m there, then m will appear here. Right? So what does 0 correspond to? M equals 0, right? But if m is equals to 0, then what is the exponent? Exponent of 0 is 1, right? So there is no complex part. That's why you don't need to do anything with 0. P0, D0, whatever, F0, G0. All these functions are real from the beginning, and so you don't need to combine them. Now, p plus 1 and p minus 1, they correspond to the exponent of plus minus I with 1 phi, right? And that's the complex exponent. That's why we combine them together here. This is n equals 2, L equals 1, m equals 1, and m equals minus 1. We combine them together, we get the real part. So that's why p plus 1, p minus 1, we need to add them or subtract them, like in this case. And we get px and py. That's why. Because it all starts with this operator and its eigenfunctions. Okay? Why do we combine them besides the... Why can we combine them? I guess that's a question you may ask. Because in the beginning, we talked about this. You take two eigenfunctions that correspond to two different eigenvalues. You combine them, you will not get eigenfunction anymore, right? So here you can combine them because they correspond to the same eigenenergy. All right, so this diagram that I was drawing, that levels of the hydrogen atom, right? They go 1s. You can even mix 2s and 2p in hydrogen atom because they are all eigenfunctions for with the same energy. And the energy will be minus 1 over what? 2. What about 1s then? It's 1 over 2 with minus divided by n squared. So n for 2s is 2, or yeah, for 2 squared. Right? So overall, this energy becomes minus 1/8. Right? And you can mix them all. Yeah.
Can you go back up a bit? So why is there a factor of I, like 1 over I root 2 in the second
This one?
not in the first one?
That's because if you just think about what is cosine and sine, because that's what we're getting. How do you get cosine function out of two exponents? You take them, plus I phi and minus I phi, right? That's your cosine. But if you want sine, then you cannot just subtract them, because subtracting them will give you 2I sine phi. From the earlier expression, you need to divide this by 1 over 2I. Okay? So this is just from the earlier expression what exponent of I phi is a cosine of phi plus I sine phi. Right? So you need to get rid of this I. If you are subtracting two functions with different imaginary part, then you ended up with the imaginary part, so you need to divide it by I in order to get the real function. That's why it's divided by 1 over I. Okay, so, and as I was saying, the pz was from the beginning without any phi, right? And these are the functions that you've seen already. Real orbital. As you can see here, the real orbitals are not eigenfunctions of Lz. Okay? Why is that? Right, so the real orbital, like here, cosine, right? And if you consider d over d phi, that's the LZ operator. This constant is not changing anything. But essentially, if you apply d over d phi to cosine, you will get what? The answer is right here. Right, so with minus sign you get minus sine phi. So then cosine is not an eigenfunction of Lz. Why is that? Well, because it's a sum of eigenfunctions of Lz, but with a different m's. One is plus 1, another is minus 1. You add two eigenfunctions with different eigenvalues, you will never get eigenfunction. Okay, so that's why real orbitals, they are not eigenfunctions of Lz operator. Okay, but they're still eigenfunctions of h and L square. Okay, this is kind of a situation like with kinetic energy and momentum. Every eigenfunction of momentum is an eigenfunction of the kinetic energy operator, but not every eigenfunction of kinetic energy operator is a momentum eigenfunction. Because of the degeneracies again. Real valued 3D, it's the same idea. You just add together the functions with plus and minus m in order to get rid of the exponents. And that's the procedure. That's how you build this dxz, dyz, x square, y square, so on and so forth. Right. These are the orbitals. It was kind of surprising for me when I was studying, just in the beginning, chemistry, about these orbitals, that for some reason there was dz square, but there was no orbital like 3dx square or 3dy square, but there was a 3dz square. Right, so the reasoning for that is just comes out of, well, what do we call z coordinate? Historically, we just like to work with the z coordinate, and that's why we separated everything along the z, like Lz operator, and we just historically, I guess, we called 320 as a 3dz square. That's why there is no reason to add anything to this zero component of Lz, while for the x square, y square, we need to make a combination in order to make a real orbital. Okay. And also the names, they partially come from, how do we think about x and y in terms of spherical coordinates. That x, it starts with the polar coordinates. X is r times cosine phi, while y is r times sine phi. And the spherical coordinates have their own notation. So from that notation, essentially, this angular part translates into the name x squared minus y squared. This angular part translates to the name xy, right? Have you ever thought about this? Like, why are they called? Well, if you look at the pictures, then you can see that whatever numbers, like, or whatever letters they have, xy, for example, they are just in xy plane. You can relate to that. Now, here's the f orbitals. And then these nice pictures of actually experimental detection. If you take the hydrogen atom and in the ground state and you start diffracting something, or, well, I don't know actually what did they use to generate these pictures, but or some kind of measurement process. So then every measurement where electron is in a hydrogen atom in 1s state, it produces this small dot, right? And they need many, like 20,000 snapshots. That's what is written here, right? So they did 20,000 snapshots on completely identical 20,000 systems, and every time they were getting a different result because, well, the position of electron is uncertain, right? So because the wave function that we obtain in a hydrogen atom, it's an eigenfunction of H, but it's not an eigenfunction of, say, R operator or X, Y, or Z, right? So that's why the probability density is redistributed like that, 2s, 3s, and so on and so forth. Now, there is no way you can plot the orbitals themselves. It's always probability density. Keep that in mind. Well, another actual reason for that is there is a mathematical reason why we cannot obtain the wave function in experiment. It's because if you think about time-independent Schrödinger equation, right, then you can multiply wave function by any number. Simple example would be -1. We would be still eigenfunction. If you have an eigenfunction psi and you change the sign, kind of make minus psi, we would still be eigenfunction. Why? Huh? But here we need scalar to commute with Hamiltonian, right? And it does commute with Hamiltonian. So yeah, you can multiply by minus. That minus can be taken outside. H acts on psi, right? The idea would be, if this is the case, then you have H minus 1 psi equals to E minus 1 psi. You want to check whether that's true. You can take a minus 1 here, and this is indeed E psi, and multiply by minus 1, right? And that's what this is essentially. So you can multiply function by minus, or in general, in order to avoid ruining the normalization, you can multiply function by a number like of this kind. By any phase, complex phase, this will be cosine of phi plus I sine of phi. And phi can be any number, well, between 0 and 2 pi. Because, well, when you go beyond 2 pi, they will start to repeat themselves. It doesn't really matter. 3 pi is the same. It will make the same effect as just phi equals pi, right? But the idea here is that all these numbers, by absolute value, they are all 1. And so you can multiply them, any of them, to psi. And if psi is normalized, then psi tilde also will be normalized. But the way psi tilde looks is completely different. All right? If you plot psi, just give me any function you like. Say x squared, right? And so if I multiply x squared by I phi, what do I get? I get x squared multiplied by cosine phi plus I sine phi x squared, right? So I'll have a real part, which is x squared multiplied by something which is lower than 1, right? So essentially I get alpha x squared plus I'll get some beta constant, which is sine phi, and that's the imaginary part. So this function will look, if you plot it, will be different. So the x squared, say, looks like this, but this guy, it has, first of all, imaginary part, which you need to plot separately. But if you look at the real part, it has a different coefficient, so say it looks like this, right? So the function will look differently. but it's still an eigenfunction of the, if x squared was eigenfunction of the Schrödinger equation, then this guy is also eigenfunction. And it's also can be probability density if you square it take an absolute square. Okay. All right. So that's all for the solution of hydrogen atom. And would you like to make a little break, or should I continue? Because we have half an hour at least. Break or break? Okay, let's take a 5-minute break. Okay. Okay, so let me tell you, or rather remind you, how to do calculus in spherical coordinates, because some questions about hydrogen atom, essentially how much of the probability density is within a certain radius, will end up taking some integrals in the spherical coordinates with respect to radial component, and I'll just try to tell you how it's done. Now, this we discussed at some point, but just with these pictures, I think it will be useful for you to remember that if we're interested, say, taking an integral of some function in the Cartesian coordinates, then there is a function and there is an element of space, right? Infinitesimal element of space, dx times dy. But for visualization purpose, you can make it finite but small, right? And no matter whether you take dx dy here or here or here or somewhere, wherever you like, right? The system is Cartesian and the dx times dy will be exactly the same. Now, in the polar coordinates, still 2D, but now we have a radius and angle. It turns out that radius and angle, if you look at the element of space in those coordinates, depending on how close you are to the origin, this element can be larger or smaller, right? And naturally, you would expect that it will be larger when we are farther from the center and smaller when we're close to the center. And that's exactly what we see if we look at, if we skip the math for a moment. The right expression is r times dr times d phi. And how do we get that? The idea is very simple, and we talked about this in the context of determinants. What we can do is we can represent these dx dy orthogonal vectors using a chain rule with the vectors, elementary essentially vectors of along the phi and along the r coordinates. And the coefficients here will be, or kind of can be thought as actually a matrix, because it's like 2 by 2. It's a matrix which is called Jacobian. And if you want to say represent these coordinates as like an orthogonal set of dx dy, then you would use the inverse of that matrix. But long story short, if you have essentially new vectors d phi and gr that are non-orthogonal, then in order to find the area of the space, you would take the determinant of the coefficients of those vectors, right? And the determinant of Jacobian in this case, as you will find out in the homework, or already did, I don't remember. Jacobian is asked to be calculated in the current one or the one that was before? Current one. Okay, so yeah, some of you will find out. Some of you already found that Jacobian for 2D case is just R, and then naturally this area fragment must be augmented by this R part, which kind of makes sense from the picture as well. But from the picture you cannot really tell whether it should be R or R square or R cube, right? You know that it should be some positive power of R, but which function of R? you don't know. That Jacobian kind of tells you exactly what it should be. Now, when we go to the spherical coordinates, situation is very similar, but we have now a little bit, one more degree of freedom. And Jacobian at the end becomes r squared times sine theta. Now, r squared, or some positive power of r, it's expected because, well, kind of again the same effect. You come close to the center, then you get smaller fragments. Because the fragments, and like we're talking about volume now, and this is like r squared because we are talking about well, surface area, then it naturally appears as r squared. But one sine theta here is because when we go to the North Pole or South Pole, you can see that the segment becomes kind of more and more narrow. If theta becomes close to 0 or pi, then the sine becomes close to 0, essentially, right? And that's what you would expect, because if you consider fragments which are closer to North Pole, then all of them essentially end up being just one point, right? So when you have theta close to 0, they should disappear, and that's what Jacobian is doing here. It has this theta factor, sine of theta factor, right? And naturally you have dr, d theta, and d phi. Okay, so any questions about this? You can either remember this, or you can think of the determinants and all the chain rules. You can obtain this. Jacobians are usually very useful, especially if you transform from one coordinate system to another. Okay, now where do we use them in the hydrogen or hydrogenic atoms? Okay, so when we need to normalize function in the spherical coordinates, we would do that in the Cartesian coordinates by just putting this integral to 1. Now, in the spherical coordinates, you have also three integrals, function, squared, but there is also Jacobian. Okay, and just also mind that say radius goes from 0 to infinity, then phi goes to from 0 to 2 pi, and theta goes from 0 to pi. This is radius, this is theta, and this is phi. Okay. Now, what people like to use for presenting the probability density plot is they like to integrate out or remove all the angular dependencies, right? And just see how, like when we far from the nucleus, how the probability density decay with distance. And of course, we don't just toss out theta and phi, because some orbitals and some wave functions, then they have angular dependence. And so then you need to just sum, average over all angles, essentially, accounting for the Jacobian part that depends on angle, right? So this is this d and l of r part, and it is formulated like the integral over angular variables, right? The r variable is essentially not touched, and also the part of this radial probability density is r part of the Jacobian. That's why then later we can just integrate the d over radius without adding r squared, right? So because we already defined d with r squared, so this integral can be written as a 0 to infinity dr, right? So very simple form. And this integral, of course, is 1. Now, what we're getting to is, say, the size of atom. If you are interested in defining the size of atom, and if you want, well, the most diffuse part of atom is, of course, electron, right? Now, you cannot, if you say, okay, my atom is the radius, big R, where d of r is equal to 1. So what this big R should be then? It's a very simple question. I'm asking, if you have this d of r radial distribution function, and for normalized wave function, if you take the integral from 0 to infinity, it's equal to 1, then you ask, okay, I want to define the size of my atom, and the definition of the size would be the radius. And the radius, if it's big R, then the integral from 0 to big R of dr equals to 1. So based on this definition, what the big R should be? Infinity, right? So this is not meaningful. Well, at least you will get the infinite atom all the time. Now, this is not realistic to get something finite from R if you put 1 here. But you can be less greedy and say, okay, well, if I want to encompass in this sphere of radius R, say 99% of the atom, right, of the electron density, so then there is a chance to obtain R which is finite, right? And this R will be kind of the characteristic of how big of the atom is, right? Then you can compare one atom to another atom, or one orbital, or kind of one atomic system that populates a certain orbital with another atomic system that populates another orbital based on their big R's, but the amount of electron density that these big R's will encompass, it must be the same, so that you compare apples to apples, oranges to oranges, right? But this functions d of r is a convenient function to define the size of the atom. It just requires having what the integral is equal to. Okay. Now, this is a little bit of more algebra here, because if we're talking about hydrogen atoms or hydrogenic atom wave functions, right? So they all have this form, the radial part times the angular part, and if we put this definition inside the definition of what dNl is, the radial density, then we integrate only the like angular parts, right? And they integrate to 1, because the spherical harmonics, they are essentially normalized functions, orthonormal functions, I would even say, because they are eigenfunctions of the Hermitian operator L square, right? So that part is just 1, and the dNl of r then becomes just a very simple expression, r squared times big R squared NL, right? Now, because of this small r squared, there is an interesting effect shown here, that the radial part itself for 1s orbital, for example, it exponentially decays, right? So the highest probability, according to just the radial part, is to find the electron on the nucleus, right? But the nucleus is very small itself, right? So if you multiply by this part of radial part of Jacobian, again, the closer you are to the center, the elements become very small, then, well, it goes to 0 essentially here, right, at 0. And if you account for that part, then the kind of the probability density becomes looking more like Gaussian, right, which has some optimal kind of distance from the nucleus. So you have two competing effects. One is that the farther from the nucleus the radial part exponentially decays, but then the size of these elements of the sphere that you're integrating over, it becomes higher and higher, like larger and larger with r squared. So therefore, there is a sweet spot somewhere, which is actually called atomic Bohr radius, right? So this sweet spot, as we will find out, is related to atomic Bohr radius. Okay, and here is some. What is this? This is a consideration of the radial parts. If we have different radial functions, during the break you asked me where do we get these radial functions. They are tabulated. There is, oh, I don't provide here any simple expression. Whenever you asked something in the exam or homework about the radial or angular part, I always provide you the function. I don't expect you to remember them. And maybe there are expressions like with the Hermite polynomials. There is like more or less compact expressions for these functions. There are possibly also expressions I'm just not aware, and don't feel that it's necessary to provide those expressions, because whenever the problem is set, then I usually provide the functions. Okay, so these functions, the radial functions, squared and integrated with r squared, the integral is 1 because the functions are normalized. Just don't forget about this small r squared. And the way they look, I don't know whether in general chemistry they showed you, but essentially this is the kind of the 1s orbital has an exponential function, no decay. Then 2s orbital has a nodal node, right? That's the point where the function crosses the 0 line. And then 3s has 2 nodes, 4s more than like 3 nodes, and so on and so forth. The number of nodes kind of related to n as n minus 1. So then here in the case of p orbitals, we start with nodeless function, and then we're getting node in 3p and so on. And also you can see that there is a maximum that goes from the 0. If you go maximum in s orbitals, 1s is essentially, and in others as well, it's at 0. In p orbitals, the maximum of the function is somewhat already at the distance from the 0, and with d and f, it's farther and farther from the distance. So the functions become more and more diffuse, in other words. And this is comparison between the radial function itself and the radial distribution. As you can see already in 1s function, radial distribution is separated from 0. Then 2s, 2p, you can see characteristic behavior here is that 2s, for example, the second maximum is larger, right? So that's why they, like if you have 2s orbitals, they have longer bonds, and then 3s is even farther from the center, from the nucleus, where the maximum is. Okay, and continuation of that for d. Maxima just become further and further from nuclei, and then the larger the difference between n and l, then the more nodes you have. And this is all in one scale, 1s, 2s, and 3s. The same with p and d. Okay, so now we have this already, they integrated, and now let's consider this problem. Show that the 1s electron is most likely to be found at the distance which is equal to the Bohr radius from the nucleus, and the 1s orbital is given. Okay, so in these problems you need to be careful what is asked. The question here is that the electron is most likely to be found at the distance. So that means most likely means that the probability density is the highest at this distance. Okay, so you need to find what's the probability density function of the distance is for this function, right? And how do you find the maximum of the known function? You differentiate and you equal the derivative to 0. So let's all just try to solve this problem. So all you need to worry about is the functional part. Don't worry about the constant. Okay. So what is the d? D of r will be function, the radial part squared times r squared. And so the radial part is the exponent of minus r divided by a0 squared r squared. That means the exponent squared to r a0 r squared. Then we differentiate. Okay, so everyone is familiar with differentiation. So all I did here is square the exponent r squared, then I differentiated. First I differentiated r squared, it's 2r, then I differentiated this exponent, minus 2a divided by a0 is appeared, right? The exponent, then r squared, and so then this can be presented as 2 divided by r, because there's 1 power of r here and 2 powers of r in this case, right? So if I want to put outside of the bracket exponent with r squared, then this part will be 2 divided by r, and then minus 2a0. So for this thing to be 0, either r must be going to infinity, right? Then exponent is 0, or r is equal to 0, or this is 0 essentially. Okay. And physically, we know that if r is infinite, then this function is 0, so maximum cannot be at infinity. Also, maximum cannot be at r equals 0. The reason we are finding these infinities and zeros is because when we take derivatives and put it to 0, then we find an extrema. So it's not necessarily maximum, it could be minima. So r equals 0 and r equals infinity those are minima in the distribution, and only if this bracket is 0, which corresponds to r equals a0, then we get maxima, and that you can see by just looking at the what does dr look like. So the point is somewhere in a finite region, so based on this consideration it should be at a0, and that's the solution in notes, right? At the same distance. Now there are some mathematical tricks that are useful to find. If you asked what's the average distance, right, then we need to calculate integral of with the operator, which is r here, and to calculate those integrals, there's a general expression right here we can use, and then easily using this expression where x should be substituted by r and n by 1, you can kind of, or sorry, the n should be 3. I'm looking at the wrong expression. All right, n equals 3, then you can just use that expression and obtain that the average distance between the electron and the nucleus in 1s state is not anymore Bohr radius, but 3/2 of the Bohr radius. So it's just a different way of thinking of the most probable distance, using the average of the operator or maximum of the distribution. Okay? Any questions? All right then, I'll see you on Wednesday. That's it for today.